The universe is a trillionth of a trillionth of a trillionth of a second old. The temperature is 1,000 trillion degrees. The infant universe inflates far faster than the speed of light, pumping vast amounts of energy into space. But the cosmos is still just the size of a baseball.
Inflation says that for a brief period, empty space gets energy. And it turns out the universe keeps dumping energy into space to produce everything we see. And so apparently, you produce an incredible amount of stuff from nothing without violating the laws of physics. It's almost magic, but that's the key word, almost. It's allowed by the laws of physics.
As inflation ends, the brightest flash in history floods the cosmos with radiation.
During the first second of the universe, it was unimaginably hot and dense. It was basically a ball of energy.
It's not a place you'd want to stand in. You'd vaporize pretty quickly. Everything's zipping round at the speed of light.
This universe full of radiation is nothing like our universe today, full of stuff, material stuff.
Because it was so hot, atoms didn't exist. Matter as we know it didn't exist. The universe was a dense soup of radiation.
The earliest universe is a chaos of pure energy. How does it transform into a universe of matter? To answer that question, we have to turn to Einstein and a very famous equation. E equals mc squared.
Before Einstein, people said matter is matter, energy is energy, and never the twain shall meet. Along comes Einstein and says, not so fast. They really are the same thing.
Einstein realized that matter is just concentrated energy. This insight transformed our understanding of the universe and allowed us to unleash devastating destruction.
Energy, E, that can turn into M, matter, and vice versa. Even a small teaspoon of matter would be enough to unleash the power of hundreds of hydrogen bombs.
While atomic bombs convert matter into energy, in the Big Bang, energy starts to turn into matter. But it's nothing like the matter that makes up the world we live in. So what does this primal matter look like? This is the Brookhaven National Laboratory in Long Island, home to the Relativistic Heavy Ion Collider, or RHIC for short. Here, they recreate matter that filled the embryonic universe 1/1,000,000th of a second after the Big Bang.
In a sense, RHIC really is a time machine. We're reproducing the conditions that existed in the early universe on the order of 1 microsecond after the Big Bang.
RHIC fires gold nuclei around a 2.5-mile circular tunnel 78,000 times a second, almost the speed of light. Then it smashes them together in a giant star detector. Imagine smashing 2 cars together in a head-on collision and working out what the cars looked like by analyzing the debris thrown off. That's what the team at RHIC is doing. They're hunting for the building blocks of protons by smashing them to pieces.
Each collision that you see here, you can see that they're different. Some collisions have more tracks coming out of them. The curved lines represent, in fact, they are the particles that come out of the collision. And you can see each collision generates a different number of particles depending on the violence of the collision.
What Mike and his team see is a spray of the most fundamental particles of all, quarks. Quarks are normally bound inside protons and neutrons, but give quarks enough energy and they break free.
We expected these quarks, once they're liberated from the protons and neutrons, not to interact much with each other, just to stream out into our detector. What we found was the most perfect fluid that was ever discovered, ever measured on the planet. So it actually flows much more easily than water does. This was absolutely surprising.
And Rick shows us that perfect fluid of elementary particles occurs at just 1/1,000,000th of a second into the Big Bang. But it doesn't last for long. As the universe expands, it cools, and something called the strong force makes its presence felt.
The most important characteristic of the strong force is the confinement of quarks inside protons and neutrons that we see as today.
When the temperature of the universe drops to 2 trillion degrees, the strong force clumps quarks together in groups of 3, making protons and neutrons, the building blocks of atoms. The universe begins to take the form we know today. But as matter is bursting into existence all around the universe, there's still something missing. Somehow, this matter has no mass. The matter in today's universe has mass. On Earth, we feel it as weight. In space, objects can feel weightless, but they still have mass. If this astronaut had no mass, he'd be in big trouble.
You can't actually slow something down if it doesn't have any mass. If something doesn't have any mass, it has to move at the speed of light. There's no way of stopping it. So a universe that's full of matter, but matter which has no mass, is one in which it just looks like a big ball of light.
The earliest universe had no mass, just elementary particles fizzing at the speed of light. But today, our universe is full of planets and stars that clearly have mass. So where does mass come from?
Apparently, there's some field that permeates the entire universe, and different elementary particles will interact with it in different ways. And it's the interaction of the particle with the field that gives the particle its property that we call mass.
Scientists call it the Higgs field after Peter Higgs, one of the first scientists to propose it in the 1960s. The Higgs field is invisible. It stretches throughout space and is accompanied by a fundamental particle called the Higgs boson, which interacts with particles of ordinary matter as they pass through the field. The more an object interacts with the Higgs field, the more mass it gains. Without the Higgs field and the Higgs boson, there is no mass. The Higgs field is a beautiful idea, but does it really exist? There's only one place to find out, at the biggest and most advanced machine ever built, the Large Hadron Collider at CERN. Joe Incandela hopes to prove the field exists by smashing a Higgs boson out of the shadows.
So I actually need all of you, including the cameraman, to go through when the other door is open. Just go all the way through. There you go. We're going down 90 meters, which is about 300 feet, about 25 stories. It took a couple of years, actually, to engineer the layout of just the cables. And there's enough cables to go from here to Moscow. And this takes us to the detector itself. So here we are. Like something out of a James Bond film. Yeah, only this is real.
The LHC fires 2 beams of protons around a 17-mile concrete-lined tunnel, which collide at the highest energy ever created by science.
equivalent to shooting knitting needles from either side of the Atlantic and having them hit head-on in the middle.
The collisions shatter the protons into a spray of new particles, including perhaps the Higgs boson. Joe's team of 3,800 scientists spend 5 years searching for the trail of particles the Higgs should leave in its wake.